Life on Earth goes way back. But how did it begin? And why here? Some believe it arrived on a meteorite. Others claim it began in a warm pond on early Earth. In 1953, one scientist shook the world when he proposed an answer: primordial soup. But was his theory correct? Now, researchers from Denmark to Hawaii are racing to understand how life may have begun by creating it themselves. Each hopes to be the first to find the origin of life. Three teams of scientists from around the world are attempting a revolutionary first: producing life from scratch in their labs. Dr. Steen Rasmussen is the team leader in Denmark.
That's very good.
We mix organic and inorganic components, a little bit like the alchemist in the old days trying to make gold. We try to make materials self-organize in such a way that it's able to become alive.
In Hawaii, biochemist David Deemer believes the key to life is to find out if DNA can assemble on its own, outside of a cell.
And if we're really lucky, we will see some synthetic reactions go on, where small molecules join up to become larger molecules. And that would be the most exciting result of all.
And at Harvard, Dr. Jack Sostak's team is trying to install a working genetic code into a primitive cell.
We know how to make these go through multiple cycles of growth and division. So really the big step is combining that with some genetic material that's also replicating at the same time.
Theirs is a race to unlock the very key to our world. But to figure out how life begins, scientists first need to find evidence of when it began. Geologist Minik Rosing has come to Greenland to find clues to life's beginnings. He searches the ancient rocks beneath the vast ice sheet. Preserved for over 3 billion years, these rocks are among the oldest in the world. Archives of early Earth. They're exposed for just a few weeks during the summer, when snow and ice temporarily retreat. So Rosing has a short time to collect samples before ice reclaims the land. He begins his search at a remote place called Isua. He's on the lookout for unique rocks called pillow lavas. These rounded rocks formed when magma erupted and cooled on the ancient ocean floor over 3 billion years ago.
When you walk out of the helicopter, and you can see these pillow-shaped objects. And when we look at these sediments that settled on top of the pillow lavas, they are also similar to sediments you find in the oceans today. So that gives us an idea of where we were at that time on the planet. We are out in the oceans.
Earth's early seabed was pockmarked by spewing hot magma. And it's still happening today. When that 2,000-degree molten rock hits the cold ocean water, it cools rapidly, creating a rounded, rocky shell, a pillow shape where sediments eventually collect. These ancient sedimentary remains are just what Dr. Rosing and his team are after. They could contain evidence of life's origins.
So what is it exactly we're looking for now?
The origin of life.
Right.
And so that outcrop down there is the outcrop that has the evidence for the earliest life on this planet.
Wow.
The team will secure samples not only from the surface, but also more than 300 feet below.
Where would the drill go down if you start right here?
We can have it so that your casing would be started here.
Yeah. So the drill would probably right there or someplace.
A core drill will extract 1.1 tons of rock samples using a 115 horsepower diesel engine. an engine large enough to run a bulldozer. Once that engine is secured atop the outcrop, it spins a hollow rod holding a drill bit encrusted with razor-sharp diamonds. Workers force water between an outer casing and the rod to cool the friction and flush out the shavings. After several days, they fill dozens of wooden boxes with samples of some of the world's oldest rocks.
We are done. Thanks a lot. This is going to make a lot of people happy.
They shipped the precious cargo 2,000 miles east to Denmark's Natural History Museum in Copenhagen for analysis. Among the samples, Dr. Rosing selects one rock formed from silty black layers of clay on the ancient seabed. To find its exact age, he crushes a piece, extracting tiny minerals called zircons. No larger than grains of sugar, zircons are like little time capsules.
How is it going?
When they form, each zircon captures a bit of uranium. As time passes, uranium atoms decay and convert into lead at a known rate. So, by determining how much lead is present relative to uranium, the team can estimate the sample's age.
So now we are more or less ready to zap the thing with the laser.
A laser burns a tiny hole into the zircon, 1/3 the size of a human hair. That releases a bit of the lead and uranium as superheated gas. The gas then flows rapidly into a mass spectrometer for analysis.
3.787.
This sample is nearly 3.8 billion years old.
That's great. That's an old age. That's really exciting. That's very, very good. That's the sad thing. You find a really nice zircon and then you just immediately destroy it and drill a big hole in it.
This rock is among the oldest ever found on planet Earth.
When you hold this rock in your hand, first of all, imagine that it has experienced about 1/3 of all time that ever existed. But also it carries a memory of the conditions in the ocean 3.8 billion years ago. So by studying these fine layers we have here, we can say, okay, what fell into the ocean? Were there any activities in the ocean? Were there life?
To find out, Dr. Rosing slices a sample so thin it allows him to look right through the rock's layers under the microscope. The geologist finds something astonishing. Tiny black grains.
What we can see here at very high magnification is some fine layers in the rock, and we can see tiny little particles of something black. And by closer inspection, it turns out that that black material is carbon.
And there's a lot of it, which indicates the presence of billions of tiny cells. The basic form of all life. Once, these tiny single-cell organisms drifting in the water were alive, taking in nutrients, reproducing and then dying, dropping slowly to the ocean floor and decomposing into their final form, carbon.
That was really exciting because you don't normally find pure carbon in sediments unless it is derived from living organisms. So this was the first hint that there were life at that time, that we agree that these are signs of life.
It's the earliest known record of life on Earth, setting back the previous fossil record by hundreds of millions of years.
From just the fact that this rock is so rich in carbon that it's completely black, it tells us that the life was efficient, it was good at producing organic matter. And the only way you can basically do that in the open oceans would be if you live up in the upper few meters of the ocean and you use solar light for energy by some mechanism of photosynthesis.
And photosynthesis, a process that transforms sunlight into food, indicates advanced life. So, scientists believe the first life likely goes back even further, to nearly 4.4 billion years ago. After a rogue rock the size of Mars hits early Earth about 4.5 billion years ago, it expels molten rock into Earth's orbit. Then, in just 1 month, that orbiting molten rock sticks together, forming our moon. Not long after, meteorites bombard planet Earth. They carry hydrous minerals, compounds that release water upon impact, and form early Earth's oceans, providing the earliest opportunity for life.
The meteorites have the same composition of water as the oceans on Earth. Oceans were established 4.4 billion years ago, and the water that is now in the oceans has been here since that time, basically.
Along with hydrous minerals, it's conceivable that life, or its building blocks, also could have hitched a ride to Earth on a meteorite. It may have happened as recently as 1969, near the town of Murchison in the Australian outback. There, funny-smelling meteorites older than Earth itself showered down across 5 square miles.
They are the fundamental building blocks of the Earth and of the solar system as a whole. The work that we do on them today won't be the final answer. There's a lot more work to be done in the future as techniques improve and new things arise.
The meteorites didn't hold life, but their odor came from something common to Earth: organic material. Under greater magnification, scientists discover that the rocks are coated with amino acids, carbon-based molecules that are among the basic building blocks of all life. But what conditions created these molecules in the first place? And how might they, in turn, create a living organism? Such difficult questions inspire scientists and artists alike. The popular video game Spore imagines if meteorites carried more than just amino acids, but sidesteps the question of how life may have been created in the first place.
We kind of basically punted on the origin of life question, and at the beginning of Spore, you actually see life, arriving on the comet, and it crashes into the ocean, and little shards of it come off, and down in the ocean, all of a sudden, a little single-cell organism pops out and starts swimming around. That's the beginning of the game.
There is as yet no proof of alien life having arrived on planet Earth. But one question remains. What conditions on Earth or elsewhere enabled life to first emerge? Before life, there was no oxygen or ozone layer in Earth's atmosphere. Instead, Earth's non-oxygen or reducing atmosphere likely held some ammonia and methane, water vapor and hydrogen from evaporating water, and lightning due to friction from the heated gas. In 1953, chemist Stanley Miller designed an experiment approximating those conditions to see if life could emerge. He zapped a beaker full of early Earth's likely atmosphere: methane, ammonia, hydrogen, and water vapor, with a bolt of electricity. He called it his spark discharge experiment. Miller's former graduate student, marine biologist Jeffrey VIDA, was there from early on.
Well, this is the original design of the spark discharge experiment. You've got this flask here, which is simulating a hot evaporating ocean. This water vapor goes up through here into this flask here. This is where the gases would be, a mixture of methane, ammonia, and hydrogen. These are electrodes that we'll use to generate a spark in the system to simulate lightning.
As the spark repeatedly zaps the vapor over several days, the vapor condenses into a liquid, flowing down like a river, back into the ocean to start the cycle again.
Liquid water is absolutely essential for life as we know it. And the reason is simple. Molecules need to be in contact with each other to have any further chemistry, and water is an excellent solvent. So it dissolves things, and once they're in solution, just by chance they're going to run into each other, and then perhaps there could be further chemistry take place.
So, did Miller create life? Not exactly. But he did create brown primordial soup, the chemical goo that pooled on early Earth before life. His electric spark broke chemical bonds in the gas. Eventually, those bonds recombined into hydrogen cyanide along with amino acids, the smallest molecules or building blocks of life. Amino acids link together to form all proteins in living things. As humans, we all share the same 20 amino acids. Miller created 5 of those 20 amino acids necessary for life. It was a first, and it launched modern scientific efforts to create life in the laboratory.
Miller started the whole field of what we call prebiotic chemistry, the chemistry that takes place naturally that produces the compounds essential for life as we know it.
But it didn't take long for the scientific community to raise questions about Miller's experiment. Many believed his premise was flawed. Early Earth didn't have an ozone layer to keep out the sun's ultraviolet rays. So its atmosphere couldn't have held large amounts of methane and ammonia.
Both methane and ammonia are rapidly destroyed by ultraviolet light, and on the early Earth there would have been ultraviolet light penetrating all the way to the surface. So all of a sudden we were back to, gee, maybe this experiment was not relevant to the Earth.
While continuing his work in the lab, Dr. Miller discovers something that changes our understanding of the origin of life forever. But the world won't find out about it for over 50 years. More than a half-century after Stanley Miller first creates amino acids, the building blocks of life, his colleague, Dr. Jeffrey VIDA, makes an incredible discovery.
We found this old dusty cardboard box and opened it up, and inside this box were all these other little boxes with little vials that were clearly labeled and associated with his 1953 experiments. It was just stunning that I'd known him for 40 years and he'd never ever mentioned this, and he'd never mentioned it to anyone.
Miller had preserved the brown primordial soup, the amino acid results of his experiments, for over 50 years. Then VIDA uncovers something even more remarkable. These results are from a second, unpublicized experiment of Miller's. Miller had met the doubt of his colleagues head-on. Initially, most agreed that methane, ammonia, and hydrogen gases existed on the early Earth. But methane and ammonia could not exist in large amounts because of the sun's ultraviolet rays. So how, then, could amino acids have formed? Miller's answer? Volcanoes. Scientists believe volcanoes formed the first land amid early Earth's vast ocean 4.4 billion years ago. And like Hawaii today, volcanic islands create their own microclimates. So when their volcanoes erupt, they spew methane, ammonia, hydrogen, and water vapor into a plume. That plume, along with ash, creates friction, causing lightning. The lightning then zaps the gases before they're destroyed by the sun.
All these gases, they would have been processed immediately, and so these volcanic islands were little chemical factories that were producing tons of amino acids, even though the atmosphere in general was not reducing, it had no methane and ammonia in it.
So Miller made a slight alteration to his original model. Instead of evaporated water entering the gas-filled chamber from the top, the water vapor now enters in a plume from the bottom, flowing directly into the lightning spark like a volcano. The first time Miller tried this, his results revealed just a few amino acids. So he moved on. But the problem wasn't in his results. It was with the limited technology he used to measure his results. So measuring with today's modern technology, it turns out the results are actually extraordinary.
What we found is this volcanic apparatus, as we call it, produced a larger variety and in some cases more amino acids than the classic experiment.
It was a major breakthrough. Yet even if amino acids were created near ancient volcanoes on early Earth, that doesn't explain how they ultimately bonded together to form a living organism. Today, that process is performed primarily by one complex molecule, deoxyribonucleic acid. We know it as DNA. Its double helix shape resembles a spiral staircase. The steps are made from base pairs of nucleotides. That's where DNA stores all the information necessary to build life. The earliest type of DNA was possibly one that could self-assemble, meaning it formed on its own outside of a cell. And if biochemist Dr. David Deamer can figure out how that happened, he could unlock the secrets of first life.
Imagine something over 3 feet long containing 3 billion base pairs. That's the amount of DNA in every cell of the human body. It's really quite extraordinary. So we're trying to figure out the simplest structure of a nucleic acid that would have the properties of DNA, the ability to replicate itself, the ability to be synthesized right from the start.
One likely candidate is ribonucleic acid, or RNA. RNA assists DNA in the building and replication of proteins in all life. But RNA's structure is simpler and more robust because it has just one strand of nucleotides instead of 2. At the foot of an ancient volcano, deep in the primordial soup, perhaps some early form of RNA self-assembled, then helped amino acids to bond together. Without the ability to self-assemble, first life could never have emerged.
Darwin himself suggested maybe life began in a warm little pond. Well, I would change that to a hot little puddle, because we now think that the early Earth was volcanic and that puddles would be pretty hot in the 70 to 80 degree range.
70 to 80 degrees Celsius is about 160 to 175 degrees Fahrenheit. Any hotter and molecules disintegrate. Any cooler and the molecules don't react at all. So this hot, confined puddle is ideal for instigating chemical reactions. But can it break down molecules at one rate and bring them together to self-assemble even faster? Fast enough to build life's complex molecules before they break down again. To find out, Dr. Deamer prepares small lava rocks with drops of DNA and RNA.
This is a reddish lava, very porous. We think that this is the kind of rock that would have been in contact with water on the early Earth.
He'll expose them to a real-world setting, inside a hot vent at the Kilauea volcano in Hawaii.
So here's the first sample of DNA. It soaks down into this porous lava. Some people think that those porous compartments are actually part of how life began, because they provided a protective compartment for some of the reactions that we're interested in.
As Dr. Deamer prepares to find out once and for all if first life could have begun in the heat of a volcanic environment, 2 more teams of scientists, one at Harvard, the other at Southern Denmark University, are pursuing the question of life's origins in a whole new way, by racing to be the first to create it in the lab. 3 teams of scientists from around the world aim to be the first to create life from scratch. In Denmark, Dr. Steen Rasmussen heads up the effort.
So how are things going?
It's very good.
I believe life can be made in the laboratory, and I think that life can be made in many different ways. I don't think there's just one way to do it. I believe that there's a variety of designs out here. Different research groups are pursuing different ways of doing it, and I think that I'll be very surprised if we won't be able to implement several different minimal or very simple living systems.
Cells are the smallest unit of life. Organisms range in size from just a single cell to trillions of cells. But at their most basic level, all cells must have three things in order to survive. DNA, the information needed to build and reproduce. Metabolism, the ability to take in food, change it into energy, and discard waste. And a membrane, a container to hold and protect it all. Like the video game Spore, the ultimate goal is to create new forms of complex multicellular life.
We unfortunately can't make anything that's like Frankenstein or what you see in Terminator. What we're attempting to do is make a life form that's way, way simpler than the simplest modern life form. So it'll be something that's a million times lighter or smaller than the tiniest modern bacterium. So it's very, very primitive life.
These magnified fatty amino acids aren't alive, but they are critical for life. Like soap bubbles, adding water to fatty acids causes them to self-assemble into round vesicles. Containers perfect for holding and protecting a cell's functions and DNA information. A container or membrane is the first step for creating life. For the Danish team's recipe, they begin with a small dash of ruthenium. Ruthenium is a rare, durable metal usually used for jet engine turbines and computer chips. And while it may not have been part of the first life in early Earth, for creating life in the lab, ruthenium is valuable for one critical quality. It absorbs light. That quality provides enough energy for basic functions in the team's simple cell or protocell. Once the solution turns orange, that means the ruthenium is mixed evenly and is ready for the next step.
We try to make our protocell from materials that are as simple as possible. We want to go from the non-living material to the living material, so we actually make this transition from non-living to living. That's the important part, and it's not so easy to do that.
A second team member prepares a test tube of fatty acids in salt water over a magnetic mixer.
Well, it's very simple. Under this plate we have a disc that turns continuously and basically is magnetized, and here we have a little magnet and that will follow the magnet.
The small white magnet provides an even stir. A steady stir ensures the ruthenium gets mixed evenly throughout.
And now I will start titrating, as we call it, adding acid to permit the spontaneous formation.
When the final ingredient, hydrochloric acid, is added, this even mix provides the best chance of assembly of protocell membranes. The cloudy texture means that self-assembly is successful. The membranes are visible only under magnification.
I can clearly see that I have formed a membrane about 1,000 to 10,000 times smaller than your hair.
This is the first step toward creating life. But there's a problem. The team must figure out how to insert life's last two elements, a metabolism and an information molecule like genes, inside. In a normal living cell, the membrane is controlled by special proteins, gatekeepers that invite what's needed and repel what's not. But creating these proteins is far too advanced for a simple protocell. So to overcome this problem, the Danish team comes up with a revolutionary idea: moving the protocell's insides to its outsides. The team chemically attaches genetic material to the outside of the membrane. This eliminates the difficulty of moving resources in and out of the cell.
So this whole monkey business of getting things through a membrane, you can completely avoid by turning the cell inside out, so that you can view your cell more as a used piece of chewing gum or Play-Doh, and then you can actually put the different components to the surface of it. So then you have your container decorated with your genes and with your metabolic complexes, and they stick. So it is a container. They contain and they make sure that these things are close to each other.
These inside-out protocells can never exist outside of a test tube. Still, even with this simple protocell, the team hasn't figured out how to make them divide to reproduce another generation on their own. A critical function for all life. But nearly 4,000 miles across the Atlantic, the team at Harvard's Life Initiative has figured out a simple solution. Dr. Jack Sostak and graduate student Ting Zhu have determined how to get their membrane vesicle to spontaneously divide without turning it inside out.
These membrane vesicles, we can make them grow and divide all by themselves. For a long time, we were just thinking about growth in too simplistic a way. We thought of starting off with a spherical vesicle and it would just get bigger.
A vesicle membrane can grow when small fatty acids, or micelles, combine with the fatty acids already in the membrane, causing it to expand. But that type of growth creates difficulty when it comes to division.
It's really hard to make a spherical vesicle divide. You have to change the shape. It takes a lot of energy.
To conserve energy, Ting Zhu developed a groundbreaking process. Vesicle division by simple environmental vibration. Vibrations similar to those from a wave or current.
The vesicles are growing and the tail coming out.
Under the microscope, those micelles are growing in a long filament stemming from the vesicle membrane.
It actually grows in this surprising way by building this filamentous extension. Eventually, everything in the round vesicle will go into a long filament.
After the vesicles grow into filaments, the team vibrates the filaments, creating new vesicle membranes.
The nice thing is that long filamentous vesicle that's forming is very fragile. And so it just takes gentle shaking to make that divide into daughter vesicles.
This is a significant step toward creating life, membranes that grow spontaneously on their own. But it's still a long way from a living being. One critical part is still missing. Figuring out how complex genetic molecules like DNA or RNA replicate fully on their own. But in Hawaii, Dr. David Deemer may be on the verge of just such a breakthrough. Scientists believe volcanoes were integral to the creation of first life on Earth. Biochemist Dr. David Deemer wants to know for sure.
Oh, look at that. Isn't that spectacular? This is just what I came for.
These real-world conditions at Mount Kilauea in Hawaii's Volcano National Park approximate Earth's early environment.
Right on the edge of the Kilauea caldera, this is a hot area as part of the volcanic activity, and this is where the heat from this magma that is driving the volcano warms up this part of the site of the volcanic area.
A caldera is a cauldron-like pit usually formed by the collapse of land following a volcanic eruption. Scientists believe when life first appeared, the Earth was full of places like this one. Here, hot gas vents emit water vapor, hydrogen sulfide, and sulfur to form a crusty surface.
Everybody used to think, and I'm sure most people still think, that life began in the ocean. But there's too much calcium, too much magnesium, too much ferrous iron on the early Earth and the ocean at that time. There were volcanoes back then, and there would be rain back then. So we now have a freshwater environment. Now you can do a lot of things in freshwater that just don't work in a marine environment. So that's one of the reasons I like to come to places like this and see what it was like some 4 billion years ago when water began to condense on early volcanic land masses.
But life requires more than fresh water. It also requires an energy source. A volcano provides that energy through heat and reactive chemicals. Dr. Deamer will test what role, if any, energy has in the breakdown and self-assembly of his DNA and RNA test samples he prepared earlier. With park ranger Laura Schuster as a guide, he searches for a hot vent with just the right conditions to place his samples. It must have a temperature range of 70 to 80 degrees Celsius or 160 to 175 Fahrenheit. Any hotter and his DNA and RNA samples will cook. Any cooler and the samples will remain unchanged.
There are a few here. We'll move up a little bit farther.
Oh, look at that. Yeah, it's nice and deep.
You see how the edges kind of collapse, so be really
I'll be very careful about that. Well, the first thing I'm going to do is to make a measurement of the temperature.
He uses an electronic thermometer with wire leads. He'll run the leads deep into the vent to see if the temperature range is right for the test.
I'm reading about 49 to 50 degrees down there, so it's just not nearly hot enough.
Not quite warm enough.
We need another 25 to 30 degrees.
Okay, well, why don't we check another hole over here?
Now I'm getting something around a little over 50 degrees again. So these are just too damp, I think. With the rain and all that we're experiencing, just keeping the temperature much too cool for the kind of chemistry that we're trying to drive.
They keep looking.
And it's protected, which is another good sign. Oh, it's hotter. Feels hotter.
This hole is close enough for Dr. Deamer to use a standard mercury thermometer.
Wow. 60. 70. I think this is going to do it. Okay, we got 75 degrees here.
Looks like this is it.
Yep. So I think I'm going to go ahead and try this one and see whether we can't get the experiment to go.
Perfect. That sounds great.
I'm happy with that one.
Very good.
Deamer retrieves the small lava samples coated with DNA and RNA he prepared earlier in his lab. Protected in tin foil and secured in a wire mesh, they can endure temperatures up to 1400 degrees Fahrenheit. He's trying to find out if vents like this one will not only break down the building blocks of life, but also assemble them again.
We want to see if any synthetic reactions occur, where molecules come together to make larger, more complex molecules, which is the most interesting, of course.
If DNA or RNA molecules do self-assemble, then Dr. Deamer will have uncovered strong evidence about first life, that it may have begun in a volcanic setting.
We're going to give this about 2 hours' time. In the laboratory, we find that that's enough time for the reactions to occur that we're interested in.
Tin foil keeps heat on the samples and prevents rain from cooling them.
So what's going to happen is the heat will build up in there. The heat activates the molecules and allows them to form links. Two molecules get together, they lose a molecule of water, and they make a link. And this is in fact what life does to grow. Well, it looks like everything's under the control here. Temperature up where it should be, and we'll come back in a couple of hours and see what we get.
If Deamer's results demonstrate DNA or RNA self-assembly, that'll be a major step toward unlocking a mystery of current life. It'll also be a monumental step closer to creating life from scratch in the lab. Hawaii's Mount Kilauea volcano may hold the secret of first life. To find out, Dr. David Deamer returns to see what effect the volcano's heat and gases have had on his lava rock test samples. He He's coated them with DNA and RNA, the information archives of all life. These samples have been baking for 2 hours in a volcanic vent at 170 degrees Fahrenheit.
There's our samples. They're quite dry, quite hot. I can't touch them. You can see these little chips of lava, each of them representing a different experiment that we're doing. And we assume that some chemical reactions have occurred under the conditions of pH and temperature in this volcanic vent.
Back in his lab at the University of California, Santa Cruz, Dr. Diemer analyzes the results. First, he adds distilled water to the samples. This simulates early Earth's rain or tides washing over the dried nucleic molecules. The water loosens them from the lava chips, providing a solution where the molecular bits have a chance to get closer and react, assembling or breaking down further.
The wetting phase stirs up everything that had been dried down originally and gives another try the next time around. So we would cycle wet, dry, wet, dry. This wetting, drying cycle is very important to concentrating the organic compounds required for the origin of life.
To find out if the DNA and RNA broke down and built up, he extracts the concentrated solution from each sample and places it onto an electrophoresis gel. The gel is an electrically charged slide that sorts the molecules by size. The bigger molecules move more slowly and stay near the top of the slide, while the smaller bits move more quickly and fall toward the bottom. Once sorted, the molecules are stained for easy visibility. In a photo, Diemer captures the microscopic results. The RNA are represented by the short, fat streaks. The DNA are the tall, thin ones.
It's really quite surprising to me that RNA is more robust than the DNA. Here's the control RNA that was untreated, and here's the RNA that was on the chip that was treated. It looks like a lot of the RNA, maybe 90% of it, has survived these conditions. And that's good because early life needed RNA to be stable at high temperatures to survive.
But Diemer wants to see more than just survival. He's looking for self-assembly, the ability of an organic molecule to form on its own outside a cell. The critical step to first life. Self-assembly of an RNA molecule in a volcano would be a major milestone. Unfortunately, the blank columns reveal that no RNA self-assembled. So Diemer, Sostak, and Rasmussen's understanding of life's complex systems all have a long way to go before a living being springs from a test tube. Now, other scientists are looking for that complex understanding beyond Earth. Using NASA's space-bound Kepler telescope, scientists are hunting for small, Earth-like planets orbiting Sun-like stars. They will examine more than 100,000 solar systems in the next 3.5 years. They hope that some of these planets orbit at distances from their sun so that their temperatures might be right for possible lakes and oceans. If rare liquid water is found, the chances of finding life and its origins are even greater.
With Kepler, we expect that in the next 3 years we will know of several dozen Earth-like planets. We will actually find out what are they made of and what is in their atmospheres, what is on their surfaces. And then finally the question is, are we alone?
But our best hope of recognizing an alien life form might come from creating life in the lab here on Earth using primitive biochemistries. We may answer the fundamental questions about the origins of life without ever leaving our planet. If the conditions necessary to start life vary beyond volcanoes and hot puddles, then life could be far more common than we know. But Dr. VIDA believes it could have also formed in ice. These frozen flasks hold many of the same brownish amino acids created by Dr. Stanley Miller's hot spark discharge experiment. Years earlier, these flasks were filled with hydrogen cyanide and placed in cold storage.
What's happening here is as the water freezes, leaves behind little tiny brine pockets of very, very concentrated solution. And this is where the chemistry takes place. And these little brine pockets can remain liquid even at very cold temperatures.
Not only could life on Earth have begun in the cold, it implies, to Dr. VIDA, that alien life might be closer than we think, in our own solar system. But not on a planet, on a moon. Jupiter's moon, Europa.
The icy satellite of Jupiter, has a liquid water ocean covered with ice. And, people are intrigued about whether there's life in that European ocean. I take a different view on it, and that is that probably a lot of the chemistry that we think took place on the early Earth producing simple compounds may have or is taking place in the European ocean now. In the billions of years in the future, when our sun swells up into a big red giant and engulfs the Earth, all of a sudden the European ocean's going to melt. And I look at Europa as a big frozen prebiotic casserole that could then undergo further processing, have a second origin of life way into the future of our solar system.
Whether scientists can unlock the secret of life's origins in the cold of a glacier or the heat of a volcano, one fact is clear. Using that knowledge to create life in the lab would change the world as we know it. Scientists believe first life on Earth emerged around 4.4 billion years ago. Now, with advances in protocell membrane growth and self-assembly, we may be on the verge of a second origin of life. And with it comes the potential to create a whole new world.